Okay, having classified various divergences in phi to the power n QFT, we shall now proceed to cure the divergences in a given theory. So divergences means that we do not have a quantitative sense of various physical quantities that we compute. And this is called the cure that we are going to study is called the program of counter-term renormalization. So this is an approach to cure UV divergences of QFT and make it quantitatively sensible. So recall the tadpole removal discussion that we had earlier. For phi cube potential, what we did is to define a shifted field phi s such that phi is equal to phi s plus alpha, where alpha is a constant shift. When we wrote down the same Lagrangian in terms of phi s, then it essentially became of the same form, same Lagrangian, but with redefined parameters plus a linear coupling. So we had initially we started out with a Lagrangian in terms of phi, which had some form, and then when we write the same thing in terms of phi s, we ended up getting same Lagrangian plus a linear coupling, which means that in the Feynman diagram we have basic elements of the Feynman diagrams are the propagator, the 3-point vertex, and a 1-point vertex. And as a result, the total tadpole became the tadpole of the tadpole diagram of the original theory, which involves only the cubic vertex loops constructed out of cubic vertex, plus this. So this is this, if you call it beta, the strength of that linear coupling, then beta is related to alpha. Now this quantity is divergent, as we now know that we have seen that primitive divergence of phi cube theory has a one-loop tadpole, and that's included in this diagram. And you can view this as a counter term which is also divergent, which means beta is not finite. However, the sum of these two, you can demand it to be 0, which means it is equivalent to saying that you are adding a constant shift, with that constant is basically a parameter that is divergent, and using that you are cancelling the divergent loop diagrams that appear in the 1-point function. So it is the similar approach for all the UV divergences. One takes a similar approach. We will not give any shift to the field, but just keep on adding such counter terms such that at the Feynman diagram level, they will cancel the existing divergences. And you modify the Lagrangian in accordingly so that this counter term diagrams are produced. Okay. So in the case of tadpole, the modification comes by shifting the field, but we do not have to shift the field. We just add new terms in the Lagrangian such that these new terms produce the divergent counter term Feynman diagrams. So the approach is you write LR to be equal to define LR to be equal to the original Lagrangian L plus LCT, L counter term. So this is sum of counter terms having divergent coefficients. And you demand that this has finite Feynman diagrams. Right. So when you add counter terms, these counter terms are also of the same form, similar form like phi to the power n. If you have a specific phi to the power n here, you have to have suitable counter terms to kill the, so that the this LR, whatever Lagrangian you get after adding this, has an effective Feynman diagrams where the divergence from the original Feynman diagrams will be cancelled by the divergence of the counter term diagrams. That is the idea. However, you cannot, this cancellation has to be done in a systematic manner. You cannot just cancel a divergent term by a divergent term. Rather, you have to regularize the terms. You have to find a regularization such that when you do a regularization, you introduce a parameter, say epsilon. When epsilon goes to 0, things should be divergent. For non-zero value of epsilon, things should be finite. And your cancellation should have should take place at the finite level, finite epsilon, where when the terms are convergent, finite. So cancellation of divergences is done by first regularizing the theory at a finite value of the regularization parameter, say epsilon. All computations using L and L counter terms separately yield finite results such that in the limit epsilon goes to 0, only LR produces finite result, while the individual contribution from both L and L counter term diverge. This is the general method, and there are many other subtleties and complications involved in it. And when we study, we will uncover those. And there are different types of regularization that one can adopt. We will study what is called dimensional regularization. Now, let us look at a particular question. So, consider a specific. If we start out with a specific phi to the power n interaction, consider a specific phi to the power n interaction. Then the question is, does LR maintain the same form as the original Lagrangian L? And the answer is no, because it depends on the counter terms which are determined by the divergence structure of the theory given by L. So for delta n greater than 0, for which we have a finite number of primitively divergent graphs, and also a finite number of non-primitively divergent graphs, there it turns out there's only a finite number of divergent counter terms that are required, and the polynomial structure of the theory remains intact. Finite number of divergent counter terms keeping the polynomial structure intact. These type of theories are called super-renormalisable. So example is phi cube in D equals 4, where the mass dimension of the coupling is greater than 0. When delta n equal to 0, then, as you remember, the set of primitively divergent graphs, although that is finite, there is infinite number of non-primitively divergent graphs, that set E, curly E. And as a result, it turns out that there are infinite number of divergent counter terms, but all those counter terms will keep the same interaction structure of the original theory. And that is called renormalisable. This type of theory is called renormalisable theories. It is 5 to the power 4 in d equals 4. When delta n is less than 0, then of course there are infinite number of divergent counter terms, but at the same time it is not going to keep the same interaction structure of the original Lagrangian, but it will lead to an infinite number of additional couplings. For example, 5 to the power 6 in d equals 4, this will lead to, the counter terms will lead to 5 to the power 4, 5 to the power 6, 5 to the power 8, and so on, all sorts of even powers of interactions. So in this case, you end up getting a theory which has, although you start out with a theory L which has only finite number of couplings, but after renormalization, counter term renormalization, you end up getting an infinite number of a theory with infinite number of couplings. So these theories, this kind of theories are called non-renormalisable. But whichever be the scenario, depending on the theory that you start out with, the fact that the all divergences of the theory can be cured, can be absorbed by adding counter terms is something very non-trivial. I mean, it is not at all obvious if a priori, and it has to be proved. And that is usually what one refers to as the counter term renormalizability of the theory. Okay, we shall next proceed to consider the richest of all these three scenarios, that is the delta equal to 0, that is 5/4 theory in D equal to 4, and do the counter term renormalization of that theory. Study the how to do the counter term as an example of explicit demonstration of renormalization procedure. We shall study this.